samtalen. Jeg tror vi tar den.
Nei, den kan vi egentlig bare skippe. Ok, så da er det streaming.
Okay, so today Carl is going to talk about C++. I want to give some information about next week, because before we can have next lab we need to talk about some more stuff, and it's okay to have that on lectures before the lab. Okay. So next Tuesday we will talk about the OpenGL pipeline, vertex buffers, vertex array objects, those sort of things. And on Thursday we will have a session on debugging. So lecture both on Tuesday and Thursday next week. And then we will start the next lab on the week after that, and then have this lab on Tuesday, lecture on Thursday, from there on out. Okay.
Does anyone need the other monitor as well? Or is that location fine? Or do you rather have it on it?
We're mostly on the right side, so I think this is good.
Yeah, because apparently you can only put the monitor on this side or this side and not on the entire thing. So as long as it's visible, then I don't.
If you need it, so.
Yeah.
So that is weird. And you can make it bigger.
Well, I can do make it full screen.
No.
Is it big enough for most of you?
Yeah, but turn off the lights.
Oh yeah, that's a good idea.
Oh.
You want some light?
Oh. Nah, más fácil. There.
Like this?
Yeah, perfect.
That's pretty nice. Okay, good. We are on. Okay, nice. So this is going to be a brief introduction to C++ for graphics programmers. A lot of you have already had this here or maybe somewhere else. Have nobody ever done C++ before? So, like, have you never done it before? Yes. Okay, so but everybody else have at least looked at it.
Oh, so what is the question? Have you done it? Or
Have you never done it?
Oh.
Or do you feel very not good enough? Yeah, well, that's okay. Nice. But okay, so we will go through the basics. So that's gonna, for everybody who have done it, it's going to be a refresher. It's not going to be very advanced, and then afterwards we're going to look at we're going to look at some modern features from C++ 11 and 14. Not really going to go into everything to 17 because you won't need all of it. And I don't want to confuse you with too much information. We're going to look at some useful algorithms and containers from the standard library that you might find yourself using throughout the semester for solving the assignments. Some general tips for this course and for C++ so you don't fall in common pitfalls. And so you can focus on the graphics programming this semester because it's not a C++ course, even though we have to have this lecture. It's mostly a graphics course, so you should use the tools available to you to make like C++ life easier, and that way you can focus more on the graphics side of things. Of course, if you want to go wild with C++, go ahead if you like the language. I'll be happy to help if you want to go wild. Some typical mistakes and then some resources where you can learn later. But we're going to start with just the basic concept, so if you have no clue what you're doing or if you will need to learn the basics, you can also pick up. So we're going to use slides and we're going to use a bit of live coding, that always goes well. So if you have questions underway, just ask and I'll try to show you. I should be able to answer everything, hopefully. If not, then I need to read more because I will be ashamed. Yes, so let's start with the basics. So let's go. First, variables. They hold a value like any language. They can mostly be of 3 different types or categories. It can be a value, a pointer, or a reference. So any value just holds the value directly. So here we have a float x that's equal to 20. All lines end with semicolons, all statements. So you can chain multiple up on one line if you want, but that's unreadable, so don't do that if you want to have readable code. Then there's pointers, which take the address of another variable, and now you can access x through y, but through a pointer. And a pointer can be null, so you can set this to null, or you can set it to null pointer, and then you cannot use it anymore. You do not know if it's null or not null unless you check it manually, or if you know. Then you have a reference, so you have float reference in this case. So now z refers to x, so this is a way of saying set is an alias for x, so it's same variable, just a different name. Under the hood, it works like a pointer, but this one can never be null. You must assign it, and if you don't assign it, you're going to have a compiler error. So
if you change x in a different value, c changes as well, or
yes, and the value y changes too. Points to will also change.
And if you change c, then you change x.
Exactly.
And
or if you change x through y, you also change x. And c will be updated because c is just another name for x, you could say.
Yeah.
That's the high level explanation of a reference. So, all of these variables can be constant or non-constant. If it's constant, you cannot change it at all. It cannot mutate it. You cannot change its member variables. You cannot change its value. You cannot change what it's pointing to. Well, actually, in this case, you can. We'll do that. And it's basically pure immutability. You cannot change anything that's constant. But it's C++, so you can if you want to. So because it's a language where you have full control. But you can cast away the constant, but you don't want to do that. So I wasn't planning on doing more on pointers and references, because if you use the language, that should be fine. Is there anyone who would like more information on pointers or references? Do so now, because otherwise you will read it yourself. Or yeah, okay, good. Everybody understands the basics, so I won't spend much time on it. Functions, pretty much standard. You have a return type and a function name with parentheses, then 0 or more arguments, starting by the argument type, the argument name, comma, and then you repeat that as many times as you like. There's a maximum, but I don't think you're going to reach it. And then afterwards you have a block indicated by curly braces, and you basically do whatever logic you want in here. You can return a value, you cannot return a value. In this case, we just sum a and b, which returns a plus b, and the result is an integer. If you have void here, then you cannot return anything a value, but you can still use return to just get out of the function earlier. So for example, if you're doing some calculations or null checks, and you figure out you can't proceed, then you can just return early if you want to, even if it's void here, but you can't return a value. Yeah, so if you're familiar, that should be fine. Classes and structs, they encapsulate data and behavior. I don't know if all classes teach this well, but there's absolutely no difference between class and struct except defaults. They can be used interchangeably and have zero difference, except that by default, when you write a class, so if we try this live, if we write a class person, and we create a variable x, is this private or public? The error messages. So yes, this is private by default. Whereas if we write a struct, it's public by default. That's the only difference.
But you don't get no error?
Yeah, well that's because it's not used, and this is public, so you don't know if it's not used. So I can turn off the errors really for this, because we don't need to see all of that.
Oh, is it a warning or an error?
It's a warning.
Yeah.
It's a static analysis warning. Well, we can have it. It's nice here. In case I screw up there. So that's the one difference, and the other difference is if I create a class student that inherits from person, and if I class add another one, class, or rather struct, or it doesn't matter really, worker that inherits from person S. The only other difference between class and struct is that when you inherit from a class, the default inheritance is private, and when you inherit from a struct, the default inheritance is public.
What does that mean?
Well, when you have a public inheritance, it means everybody else knows that your type inherits from this, but it's private, then you don't know that, so you can't use the functions of what you're inheriting from, except inside of this class, and you cannot use it in.
So you can't use any parent.
Sort of, but in 90% of cases you want public inheritance. So the only differences between a class struct and a class by default is the defaults, and you can override this and go private, and now it's like basically a class.
Right.
Or it's the same. It doesn't matter. That's the only difference. So that's important to be aware of, that you can use them interchangeably. But usually what you do is that you say, when you create an object that should hold only data, you usually use a struct because it tells the programmers that read your code that this should hold only data. It's a structure of data. Whereas a class is usually used to indicate this has behavior and member functions and other things, even though you can put that fine on the struct as well. It's usually more of a telling your intent to other programmers thing than a language difference thing.
Right.
So yeah, and you can you annotate private parts with private colon, then you have string, age, integer, motivation, whatever you want, and then you can do public, and you can use protected as well. So if you get our struct back, we can say we have a private. We can say we have a private int, x. Start initializing 10, and then we can publicly, for example, create get x that returns x. So, and you can put member functions anywhere. You can have them public, you can have them protected, or private. So this is the same as other languages in terms of how private, protected, and public work. Is anyone unfamiliar with private? Yeah.
Why were we putting the const after the function?
That is because if you don't do this, let's show the difference. So if we create data x like this, now you're just creating a variable x of type data, and we can type x.getX. That's fine, right?
Okay.
And then we create a constant data y. If this is not const, you cannot call this function on a constant version of this object.
Okay.
You cannot call y.getX because this one can change the, like for example, if this function said x plus equals 10, it would violate this object being constant.
Okay.
So unless this member function is constant, has const after it, you cannot call it on a constant object, basically. Now you can do it, because now you're essentially promising that this function is not going to change anything about this object. So now this is an error because you cannot assign to x because it's supposed to be constant within this function. So every function that does not change your class should have const after it in that case, because now you can use it on constant versions of the data as well. So that's important to keep in mind.
What's the warning or the error on getX?
It's a private function.
Yeah, it's private.
Ah.
That was just an example, but yeah, like this. Yeah, it's a text, and maybe I should zoom out a little. So we have room for more. Is this readable still? Yeah.
Yes.
Okay. Yeah. So if you have a constant member function, it can be also called on a constant instance of that class. So that's important to keep in mind. So usually all getters you want to be const, because then you can get the values from constant data types. Yes. Inheritance, we briefly looked at it. Let's look a little bit more at it. just to be so you can know what to do. So we can create. Let's go with the standard example everybody uses. Person. Let's include string. So we use a string. So we create a string that is its name, and we can say age like this. So now this person has a name and age, and let's create a constructor as well. So when you create a constructor, I mean, if something is unfamiliar, please raise your hand. I will assume that you have some knowledge about this. So we create a constructor where you take a string and where you take an integer for the age, and you initialize name to name and age to age. So yeah, I think that's not used whatever. So now we have one person where you can construct by passing a name and age. So let's create something inheriting from this. So student. So again, you have to specify that you want it to be public inheritance if you want to actually be able to let others know that you're inheriting from this. And in 99% of cases, that is what you want. Only very rarely will you use private, and that's for some compiler optimization tricks for, you know, that we will not get into because they are not needed for this course. Well, unless you want to push something. So yeah, we're going to inherit from person. So now we're saying that student is publicly inheriting from person, which basically means it is a person. So a student is a person. Let's create a function in this one as well, just so we can override it. So if we create a function that is add get older, that by default says age should be increased by 1. So now we have a get older function. Yes.
Is it called? I think it's called ampersand. In the string ampersand name, why do you have that?
That's a reference.
Oh, okay.
So we're passing the string to the constructor, one moment, as a constant reference in order to not to save a copy. Because it's usually, by the general rule is that you pass classes by constref, and integers, numbers, so int, float, all of those, you pass them by value.
Okay.
Usually, it's at least for performance. You can. It doesn't matter if you do this, except for performance.
Okay.
And you take extra copies. Yeah, there was a question there as well.
Why do we have the curly braces after the member field?
Here?
Name or age?
Here?
No, at the...
Oh, here. Okay, I see. You don't have to, but basically what that means is you construct by default you set it to the default value. So by setting mh like this is sort of the same as doing it equals to 0. Or in this case, it equals to this. It's basically just calling the default constructor. And you can't do this because then it treats this as a function declaration. So you use the curly braces instead. Yeah, so now we have a person with a function get older, which increases its age by 1. So, based on your current knowledge, can I override this function in the student?
Yes. Yeah.
Yes. Why?
Because it's public.
Okay.
It's not a constant. It's not a constant function.
Any other answers?
It's private because it's like. Oh no, didn't see it there.
Yeah. Well, let's try it. So let's go void get older, override. No, only virtual member functions can be overridden. So if you want to have a function that can be overridden in child classes, we have to make sure that it's a virtual function. So virtual means you can override this in child classes. So now we can override this and say students, when they get older, their age is increased by 5 because they're stressed by exams or something like this. But then it's a private member of person. So maybe we instead just call person get older. So you basically just do exactly the same. So, well, and maybe you just print. So now this function calls print student and then calls the parent, calls person's get older function. So if we create, let's try to run this as an example. If we create a student S and then a person P, which is called Bob and is 12, 13 years old. Yep. This line means that we don't want to create any new constructors. We're going to use the parent's constructor. So by saying using person, we are saying that we're going to just inherit and use this constructor directly as a student as well. Which means we can say
And if you wanted to make your own, then would you say
then you
student?
just create another one additionally. You can say student as well, and put whatever you want in here and create another constructor, or even just a default one.
And would that also call the constructor from the parent when you
Yes,
cross
it would, but you can't. But it will be deleted since the other person doesn't have a default one. So if you have to go person equals default as well. So now this is a default constructor which just leaves all the values at 0. And yeah, so basically now if we call s.getOlder and p.getOlder, we will have the s1 print student and the p1 nothing because we overwrote the behavior.
No.
That's a brief introduction to and repetition of this, but it was a kind of a detour as well. Let's we will get to the juicy stuff later. So. Yeah, that's inheritance. We just looked at that. You can inherit from others, implement interface or extend behaviors. So if you have class graphics student inheriting from student, you can, for example, add another member variable. You can only override virtual methods. I didn't put code in there, but we just looked at that. So make sure you put it as virtual. Also, another thing I forgot to mention is if you don't want anyone to inherit from student anymore, but you don't want, for example, a graphics student to be able to inherit from student, you could put final first. Did I forget something? There. Where is it? So, I know it's supposed to be there. This is all this is. There it is. Yes. There you go. Now it's good. Yeah, if you put final after a class name, then you cannot inherit from this anymore. That means it's the final part in the inheritance tree. And same with functions. Now you're saying nobody can inherit my function get older anymore. So if we put this up here instead, this would not work anymore. You can no longer override it.
So put it like virtual and void, like final, like overrides the virtual then.
Sort of, but it's no point in doing it here because now you're defeating the purpose.
Yeah, yeah.
But if you do it in a child class, that's when you say no, do no longer override this. Basically, you're sort of canceling the virtual. Yes.
Yeah.
I lost the slide. Good. So yeah, let's look at some loops. So you have the traditional loop that you'll find in many languages. Int I equals 0, I is less than some number, and then you increment it and do some code. You also have the range loops. So you have for auto some variable in some iterable. So basically use a colon to say in. Like in Python you would do something in something else. In Kotlin you do it equals something in a number dot dot another number. And you have a while loop, which is basically just while some condition do this or do this while some condition. So the difference is here this runs first, no matter the condition, and here it only runs if the condition is true. We'll come back to this form of loop. Have anyone used this form of loop before? The auto version? Yes? Okay. Yes. We'll look into that because it's nice later. So, if statements, if condition equals true, do something, switch on some condition, and in case 0, do something, default, do something. It's important to keep in mind here that switch only works on booleans and numbers and enums. You cannot switch on a string. So keep that in mind when you use switch. If you need a string, then you use an if statement. So let's get past all of that introduction. Now, how many of you have used features from C++ 11 or later? Knowingly. Okay, nice. Or not nice, but...
Well, maybe I've used it, but let's say
yeah, so knowingly, yeah, maybe you've used it. So.
Yeah.
Let's start with auto because it's probably one of the nicer ones that you will see a lot.
Yes.
So if you don't want to name the type yourself, you can use auto instead, basically. So this will deduce the type automatically. Sometimes it can obscure the type when it's important. So for example, when it's very important that you specify a node type, you don't necessarily want to use this. It will make some code a lot more readable. We're going to look at that when we, for example, loop through a vector or an array, or yeah. And it will protect you against error if you change the type later. So for example, if this is, imagine this function returns integer right now, then res will be an integer. But imagine sometime later, some guy comes into your code base and changes this to return a float or maybe a string. This assignment is not going to work anymore because this is now returning something else. So, but if you have this as auto, it's going to not crash because it will update what is the type of res. And so of course sometimes it can have side effects, but generally it can protect you for minor things, or when you're just testing around and you just you're just mucking around, you want just some value x to be 10, and then you're just testing, so you now want it to be something else. You don't have to go in and also change the type because you're just testing around in the first place. You had a question?
Yeah, can you put that in the function parameters? Use auto?
Not in parameters.
Nice.
No. Because then the function doesn't know what you want. For that you would have to use templates, but we're not going to look into templates today.
Yes.
Unless there's huge excitement. Yeah, so you should generally use it when it makes the code more readable, or when you have type name that is incredibly long, which we will do as an example right now. Or when the type is not important, for example, if it's an int or a float, or you don't really care about the type, just use auto and say that's what it is. There is a style going around that says encourages the use a lot, which means moving all types to the other side of the equals sign. So by that I mean you do, for example, x equals, well, with an integer that's like this, or you do s equals string some value. Basically what they think is good is that it's always auto here and the type is always on this side. So the alternative would be to do this. But, you know, that's just an opinion by some people. So do what you think is most readable, but be consistent about it. Yeah. So let's look at an example where this can be very useful. And the example is going to be when looping through something. Have you used vector before, or have you not used it?
A little bit.
Yes. But do you know what it is roughly?
No, I have not used it.
Okay, if you think about a regular array, you can have an array that is 16 elements long, for example. Right?
Yeah.
You cannot change this to 15 elements or 20 elements. Basically it's fixed at 16. So sometimes you want the pleasure of being able to add elements to an array, or have an array that scales and changes its size dynamically, like many other languages. So for this, I will encourage a stud vector, which is basically a dynamically resizable array. So you use it by saying, using stud vector, you have to include this file, which is vector. And then you have to say what's the type of the variable it should hold. So in this case, we want an integer. And then we type the name of the vector, for example, an integer vector. So now we have a vector of integers. And this is not a vector in the sense of math, that's like x, y, z, and that kind of stuff. It's more the concept of many values of the same type. So by doing this, it is now empty, it has 0 elements. So this is now the same as an empty array. We can construct it with different parameters. So if we type 10, it now holds 10 integers by default. And you can add them or you can remove them as well. If you say 10, 5, this one now holds 10 5s. Yeah, no, it's just never used.
No, would it be just 10 random integers then?
Then you would have to do more things.
All right.
Yeah. We can do it as an example,
But if you just put 10, then because I have 10 integers, does it?
No, now they're all 0. They're default.
Okay, they're also
default
default 0.
constructed basically.
Okay.
Or if it's a string, then it will be the empty string. If it's a float, it will be 0.0. So it's always the default. Or you can write, now it's 10 hundreds, basically.
Yeah.
So that's, and you can also initialize it from another vector. So if you had another vector, you can initialize it from that, basically taking a copy. But for now, or you can use the other version, which is, you can give it values by default. So that's 1, 2, 3, 4, 5, 6, 7, 8. So now this vector holds the values 1 to 8. So in the curly braces, you can pre-initialize it. This is the same as with an array. You can say array equals 1, 2, 3, 4, 5, 6, 7. So except this one can never change its size, and you cannot remove the elements. You just change your values. So unless you know that you specifically that you will forever have only 5 elements, use vector because it's just as fast as an array. It's basically 0 overhead, and it's more flexible. So you can just you can add values, you can change them, you can remove them, and we're going to look at some algorithms that work on the vector that can like sort it, find the value, partition it into 2 halves, for example, even and odd numbers and some of that stuff, which will be useful. And for example, when you get to the graphics part, you might have a vector of vertex or vertices that you will send to the graphics card. It is a lot better than having an array of them, because then you can change the number of vertices, you can remove them, you can change them, you can sort them if you somehow want to do that. So you have a lot more options basically. It's a tool that's there to be used, and you don't lose performance by using it. And if you absolutely want a raw array, please don't even use raw arrays. Do include array, and use the array instead. And say it's an array of 5 ints.
But what was the difference between if you just use R?
Well, you get some utilities. First of all the algorithms work in this container as well.
Oh, okay.
Second, you have dot size, which is nice.
Right.
You can use this loop for it. You can loop through all the elements. We're going to look at that loop now.
No, so it's what's it called?
So now we are looping through it, and we print all the values 1 to 8. Yeah.
Can we use the using namespace as the D?
I'm going to, but I would say quick answer no.
I'm guessing that is the array class slower than the vector?
No, it's if something it's exactly the same or a little bit faster.
Oh, okay.
And it's essentially just a wrapper around the regular array, but with member utility functions on top of it. Yeah.
In that for loop, can you go backwards? Or?
Not like this currently, unfortunately. But you will with C++20 because it will introduce new features to allow you for that.
When
but
is
you
that
can.
coming out? When is that coming out?
As we speak,
Yes.
it's already released, but the compilers don't support it.
Oh.
Not all of them. but not all features. Anyway, so let's look at why auto can be very useful in this case. Because we know this is a vector of integers, we could also type for every integer I in this array, just print it out, and it will print them out as normal. You could also you could also say it's a constant integer if you don't want to be able to change the value in here. We don't, so it's the same. You should prefer to have it constant unless you know you need to change it, because it will reduce the chance of errors happening. So if you know you're not going to change it, you should constant. Or you could use const auto, which means it will automatically know that it's an int, and it will become a constant int. So this sort of replaces with the type that this array holds. So if we change this to float, this code is still going to work.
Yes.
But if we still kept int here, now since float can be converted to int, that's fine. But if we put 3.5 in here, it will still print 3. So that's technically an error, unless you want to see it. If we leave it at auto, you're going to see 3.5, because it's going to know that, okay, this array holds floats. So we're going to print it as floats. Okay?
And if you do int, then it will print as an int, right? As
What?
you said. If you use const int, then it will just be like
Then
1, 2,
it
3.
Converts,
Yeah,
then it converts it to an int.
Yeah. Okay.
So since it's convertible, but if we use string here, then it would be an error because you can't convert a float to a string.
Right.
So that's why auto is nice when you're looping through, because you don't really care what the element is, you're just going to use it in here.
Yep.
So how did we loop through a container like this before auto? Well, let's look at looping through the vectors. So you would think, well, the obvious way is to just create an integer for the index, and that, sorry, I got to look at the name, and I is less than I vector size, and then you plus it, and in here you go I vector of I equals, something, for example. That's fine, but it was not the only way to do it. The other way, which allows you more flexibility in terms of looping reverse and more, is to use the iterators that come with the containers. So what you would have to write then is an incredibly long type that is vector of int, const iterator I equals I dot begin, which is the first element, and then I is not equal to I vector end, and then you plus I vector I. And now you have an iterator into the container. And what's nice about this, if you put an R before here, that's reverse begin. So that now you're looping reverse.
Alright.
Today you don't do this, you do this instead. If you want to reverse loop, you use R begin with auto I. So you don't have to type the insanely long type name. That's basically one of the other places where this is really nice.
How did the first one you just showed us? Was it auto I equals? How was the
fast version?
Yeah, the fast version. Oh.
That is I colon and then the container.
Ah, yes. Okay.
So you can use the vector or you can use the array, and that works interchangeably.
Yes.
So it doesn't care what container you're looping through as long as you can iterate through it.
Yeah.
So that's a nice use case for auto, both in terms of looping through it, and you know the type, you don't care about it in case it's gonna change, the code is still gonna work, or when the type name is crazy long, and you will have some of those. It's even worse with map or some of the other containers. So yeah. Next is lambdas. Have you used lambdas before in other languages or this language? Yeah. Okay, so basically they're anonymous functions. And they're very useful with algorithms for example, sorting and filtering. So that's what we will use as an example. And they're good for one-offs or small functions that don't need a name. For example, if you just need something to be called once, you can create a lambda for it. And they're also good for callbacks and UI. and input interactions in parentheses. So for graphics, if you're using input and want something to happen when you click the left button, for example, you can use a lambda as the function to call when you click that button. If you want a lot of functionality or want to use it multiple places, you should probably write a regular function, since then you don't, a lambda can only be sort of used that one time unless you, so for example, if we create a lambda here, so the syntax is you always start with 2 square brackets, and then technically you can go straight to the code. And in here we can write cout hello lambda. So this is a minimal lambda that you are now have assigned to f. So f is now a type of a function. So if you call f, we see hello lambda. So what this does is you always in the brackets to say hey, it's a lambda, and then there's an optional 2 parentheses in here, and then there's a curly braces to say hey, inside here is the function. So this is sort of like a regular function that you have a return type, a name, and then the parameters, and then the brackets, except that the return type comes here. So you have an arrow to indicate the return type, but you don't need it. You can remove it because the compiler will understand that this returns an integer. Only if you want to override it, you use the arrows for the integer. This is the same as the argument list, so you can write int a, int a, int b. That's the same as going int a, int b. And then in here you can, for example, return a plus b. And then you have to pass it when you call the function as well. So this is your arguments. Your return type goes like this, and then inside the brackets you have the function body. Now the curly brace, the square brackets are used to access variables that are outside of the scope of the lambda. So if we have an integer x here, which is 42, we cannot use x in here because x is hidden. It does not live inside of this scope. In order to be able to access x in here, we have to put x in here to say, hey, we are now capturing x, so we can use it inside of the lambda. There are 2 ways you can do it. You can either use the equals to say, well, that's the default basically, which means you take it by value. So by doing this, you copy x into the lambda. So now x, the lambda holds a copy of x. If you put the ampersand before it, that means you take it by reference, which means this x is the same as this x. So if you change x in here, you can change it here as well. So as an example, if we have this function, say x plus equals a plus b, and we see out x here, and we repeat it after calling the function. To make it more clear, let's just do this. With 5 and 6, we get first is 42 and the next is 53. And that happens because we captured it by reference. If we captured it by value, x would be 42 in both cases. Yeah, but you can't even change it. So because it's by default constant in here.
Oh, but you can use it to.
You can use it in computations.
Alright. So you can use it to manipulate a and b if it's not a reference.
Yes.
But if it's not if you don't make a reference on value, then you cannot change it.
Not by default.
Right.
So you can also give it an alias if you want to call it outer. You should be able to do this, or outer equals x. Yeah. And then you can x is now outer, so you have to go outer plus equals a plus b. So if you want to rename it, you can capture it by reference, give it a new name, and say what it should be equal to. But normally you don't have to do that. So that's the syntax of a lambda. It's a bit intricate, but it's very useful, as we shall see when we get to the algorithms that can operate on the containers. But yeah, you should use this I'll show you the use cases, and then it's good for, you can keep it in mind that it's good for one-offs and often for UI and UI callbacks. Or, so yeah. I don't know if we're going to go too deep into smart pointers, but I want to touch on it, so because how many use new and delete currently? Couple, yes. Ideally, you shouldn't use it. It's because it's very error prone. Can introduce memory leaks, and it's generally more dangerous than relying on the smart pointers. The only cases in modern C++ where you would use new and delete is if you're writing your own data structure, your own array encapsulation, and you really need to manage the memory manually yourself. That's why for this course we want to focus on the graphics, of course. That's why I'm going to touch on it, so you know that they exist, and I'll point you to some references where you can read more about it. But basically there are two smart pointers in C++. There's the unique pointer and the shared pointer. So a shared pointer works basically like a reference counted object in other languages, which means as long as somebody holds a reference to it, it's going to stay alive and be accessible. As soon as nobody has access to it anymore, it's going to delete itself and clean up its own memory. A unique pointer is the same, except you can only have only one person owns it. So when that one person is destroyed or goes out of scope, it automatically cleans up the resource and deletes it. So other than that, it works exactly like a regular pointer, so you have to use the arrow operator to get access to it. And I'll show some examples. But we will put that at the end, I think, and not now, just so we can focus on the stuff that is more likely to be used. Yeah, so this is the range loops. We already talked about those a little bit. So now we're going to go to the containers and the algorithms. So this can be very useful for you when working with multiple data, because graphics is a lot about. Someone described it to me once as putting a bunch of numbers into arrays and sending it to the GPU, hoping it looks nice. And that turns out to be very true. So you're going to work with containers a lot, and by that I mean arrays or some sort of dictionary map, hash map structure, or basically just a lot of data that contains it. And to operate on that data, you might need some algorithms to work on that, for example, by transforming the data, doing matrix multiplications on everything in the container, or something like that. So the standard library in C++ comes with a lot of nice algorithms that work on these containers. So that's another reason why you should look into vector a lot more, because not only is it useful on its own, but together with these algorithms, it can become very powerful. So the two probably most useful containers will be vector and map or unordered map. There's a slight difference. I'll just mention that. A vector, as I mentioned, is a dynamically resizable array, so you can add elements to it and you can remove them, and it will scale itself dynamically, and it does so very performantly. That's the purpose of it. So by far, it's the most performant container in all of the standard library. You will sometimes see someone use the list, which is a linked list. If you use this for graphics, it's basically not going to work very well, because well, if you had linked lists before, you know that they just exist randomly scattered in memory and just point to each other. When you send data to the graphics card, you want that to be continuous after each other. A list is not. It's also incredibly slow to iterate and send all the data. And it's basically a container that you never should use because it's just so slow. So if you have, unless you have extremely good arguments for using it, just always use vector if you need an array-like container. And use unordered map if you need a dictionary or hash map container, because it's faster than map. So unless you need it to be ordered, use the unordered version. We're going to demonstrate them. So
the unordered map and then map.
Yeah,
This is unordered, so when you put things in, or they just unordered, just sequentially put in
it's
some kind of like a queue?
random. an order map is just completely random, and if you loop through it, it's just the order is random.
Oh, right.
Because it uses a hash function to place it, and that.
Yeah, okay.
So it's not entirely random.
No.
Whereas the regular map uses a red-black tree, or a binary tree to order the nodes, which basically means they're always in order.
Okay.
So that's also why it's slower, because hash map is faster than the binary trees, or faster than a tree in this sense, because the tree is like a linked list as well, that it's just sort of different nodes at different places in memory, whereas the unordered map is sort of array buckets that lie together, so they're faster too. But a map might have a faster lookup, but it depends. So.
Right. And then it would just be STD, so like a map.
Map instead of unordered buckets. Yeah, so let's look a little bit more in depth on those containers, and then we'll also actually let's look at the algorithm first as well, and then play with it a little bit. So the most useful, well, some of the most useful algorithms are probably sort, find, remove, and accumulate. Sort, well, obviously it sorts the container. So, and it takes as parameters 2 iterators. So for example, if you have an iterator that's at the beginning of a container and at the end, it will sort everything. If you have an iterator at the beginning and in the middle, it will sort the first half. So we will look at that. Find is the same, so you pass the range where you're sort of going to find something, and then you pass the value you're looking for, and you get an iterator to the position where it found the elements. And accumulate is basically, if you have a vector full of numbers, you can go from the beginning till the end and just sum everything. That will just sum everything. Or you can also give it an initial value if you wanted to start at 5 or something. Yes?
The second one at find. So if you wanted to afterwards use that element, you do ivec from it, right?
Well, I'll show you when we do the live example, but basically this acts like a pointer to the element. So you have to go through the arrow operator to get access to the element. And remove it can be used to remove elements. So let's look at these containers and some using the algorithms on them. So you can.
Can I see the declaration of map again?
Yes.
Thank you.
Yeah, let's see. Yeah.
What do these K and V in square brackets mean?
We will look at it when we are looping through the map.
Yeah.
So, say, since this is graphics, let's imagine we have a struct vertex that holds a, well, let's actually include it. A vector 3 that is position, and a vector 3 that is the color. So let's say we have a vertex that holds position and color data, and we want to have a lot of vertices. So for example, let's create a vector that contains vertices, and we can call it a vertex vector.
So the GLM VSA3 is just a vector?
Yeah, it's a vector with 3 components. So X, Y, Z.
Oh, yes, I see. Okay.
So imagine this is probably something you will end up doing at some point. So
But then, because a vector, can you then resize it, like to?
no, because this is a math vector and not a container vector.
Okay.
So it's a bit confusing maybe, but that's just the way it's called. That's just the name it has.
Right.
So in this case, let's create just a loop, a regular one. Let's add 10. Let's just, so to add elements to a vector, because this is currently empty, so we're going to loop through 10 now, and we will add an element for each one. So to add something, there's a function called pushback. Pushback adds an element to the back of the vector. Some containers have push front, this one doesn't. So you can only add to the end, but you can also use insert to insert at the beginning. So for example, if you want to insert at the beginning, you have to pass the begin iterators. This takes an iterator where you want to insert an element, and then you take the element you want to insert. So we want to insert a vertex with maybe the values with 2 vectors that are both 0. but we're gonna use pushback here because we're just gonna add to the end of the container. So after this, we will have added 10 elements to the vector that all hold a 0 position and black color basically. But let's make it more interesting and use I for the x-axis and the green component. So now we have values 0 to 10 and 0 to 9 here as well. And well, we should also let's maybe print it as well. So let's look at some of the algorithms we can use on this. Right now it is obviously sorted by itself, so since we added it in order. So there's something called random shuffle that we can use to shuffle the sequence. So we want to shuffle the vector from the beginning. So we use .begin to say, hey, we want to shuffle from the beginning to the end. So now we are shuffling it. We should also probably just create quickly print vector. Don't mind this. No, let's get this out of the way. So now let's just print the vector first and after. It's called VLOOK. Yeah, so if we run this, no, it's the vertex, of course. Well, okay, let's make sure. Okay, let's not use a vertex, but imagine it's a vertex. Let's just use an integer. It makes it easier for demo purposes. So if we print it now, we should also add a. Should also add just any line. So now it's first 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it's 4, 3, so now it's shuffled. So, still random shuffle, you can use it on any container, which hold element, to shuffle them. So if you want to randomly mix something up, you can use random shuffle on a container. So what's nice about the algorithms is that they work on any container, as long as you pass in 2 valid iterators. So,
but could you, does it have to be beginning end? Can you like put like in
no,
the middle?
You can for example say begin and then begin plus 3.
Yeah.
So now you only shuffle the first element, 3 elements.
First 3
So 0, 2, 1, and then the rest is ordered.
Yeah.
So you basically choose the range you're gonna shuffle. You can also do R begin and then R begin plus 3. So now you're at the end of the container and take the plus 3 from the end. So now you're shuffling these 3 elements.
Yes.
Instead of these 3. So that's the difference between R begin and begin. So now that we have shuffled the vector and proven that that's happening, let's use sort to sort the vector again. But we want to do it onto the entire vector, so we're going to use vvec.begin and end. To sort the vector, we use a call to sort. It takes exactly the same parameters, and most of these algorithms do. They start with an iterator to the beginning of the range you want to sort, and then to the end of the range you want to sort. So by just doing this, saying sort from the beginning to the end, the vector will be, well, it's mixed up again, but it will be sorted again, basically. I'm just going to add the new line to the end here, so I don't have to do it manually. So, yeah. So now we first have a sorted vector, then we shuffle it, and then we sort it again.
Is the random shuffle always giving you the same shuffle?
Yes, because we don't see the random generator. It uses the default rule. If you want to use your own, you have to do just shuffle, but then you have to pass in what kind of random generator you want to use. So it's just for simplicity in this case. So another useful algorithm is, say you have, for example, one set of vertices that's on the negative x-axis, on one on the positive x-axis. Maybe you want to split them apart and like be able to work with them separately. Or in this case, let's say we have even and odd numbers, and we want to sort of split them on each end of the array. So to do that, we can use an algorithm called partition. And what that does is you say you want to start from, well, as usual, you go from begin to end. And lastly, you take another parameter, and this parameter is a function that you will use to say which partition should this element go to. So here is an example of where a lambda is really good to use and compare in conjunction with the algorithm, so you don't have to write a new function up here every time you're going to use an algorithm, because usually these are one-offs. So in this case, we need to take a parameter, which is the element of the vector. So this vector holds integers, so we can do int v here. And we can say that the condition to partition this, say we want odd numbers and even numbers, is that v mod 2 equals 0. So if we do this and print the vector, we now have all the even numbers in the beginning and all the odd numbers at the end. So what this has done is for us is basically partition the vector based on this function.
All right, and and the condition you put in the constant in the beginning of the array, then can you like put like so the even numbers are like the last numbers?
Yeah, but then I don't have to change this to not equals or change it to equals to 1. And then because now the condition is it's odd, so now all the odd numbers will be first.
Okay. Oh, right.
So whatever values of the container this returns true for will be at the beginning, and the rest will be at the other half. So you're basically partitioning it into two sets based on the predicates.
Yeah.
You can in lambdas there's actually one thing you can use also as here for lambdas as the function parameter type, and it will just figure out that this is a vector of integers, so v is an integer. Okay. So that's useful. You can also make this more complicated. Say if you have positive and negative numbers, that we start from -10, then you could say like if v is less than 0, then you partition it. So now all the negative numbers will be put first, and then all the positive numbers.
Yeah.
Or if you do greater than 0, then it will be positive and then negative. Except for 0. For 0. Probably because greater than equal. Yeah. So that's another one you can use. So let's look at finding an element, because that's going to be useful when working with containers. So yeah.
If you have an odd number of elements in the vector, why you partition it? How many are for?
Well, it will be if every element is even. For example, then there's going to be no change.
Yeah.
So, but if you have like 3 odd elements here, and these are even, then sort of all the even will end up on the same side, and all the odd will end up on the other side. It doesn't have to be a perfect middle split, but it will just put whatever is true on the beginning until, and actually this function returns an iterator to where the separation is. So you can actually take this value like this, and this sort of points to where the split is happening.
So if we start iterating, it will then start at the uneven numbers then.
Yeah, basically.
Yeah, okay.
So if we use a loop here, it's less than v vector n. So if we use this iterator that we get back and print it, then we can then we only print the odd numbers, because this iterator returns the point at the split. And you can use that for example, now that you have gotten this iterator points to all those odd numbers. So if you want to sort the odd numbers, you can now go sort from this iterator to the end. So that means basically we need to print the vector again. Now this is 0, 8, 2, 6, 4, but all the odd numbers 1, 3, 5, 7, 9 are sorted. So that's because you start sorting from this iterator till the end. So you have partitioned first the odd numbers to 1/2 and the even on 1/2, and then you sort just the odd half. If you wanted to sort just the even half, you would do v vector begin and then 2 int. So now you're sorting the even half. So now this is 0, 2, 4, 6, 8, and the rest is not in order. So that's how you can work together with use multiple algorithms and combine them. You can with partition and some other, I don't remember, I think. Yeah, well, with partition and one other algorithm, you can implement quicksort using just those, because quicksort is about partitioning based on a middle point and then sorting each half separately and then repeating that. So if you use partition on the other thing, you can quicksort. Although the sort basically uses quicksort by default. So.
Okay.
Some version of it, some optimized version. Like these algorithms are, developed by super smart people. So they are very optimized for their use cases.
Could you technically change it? Like if so, like when you say sorted by.
Yes, you can sort by something else as well.
Yes.
So there's another version of sort that takes a function, like partition. You can pass a function to it. You can also pass a function to sort, decide what you're going to sort on. For example, if you have a struct with multiple data, you can choose to sort on the name or on the age or on something else. So we can try to do that now. We can go sort the entire vector, so from begin till the end. And we pass a lambda as well because we don't care. Only thing is here you have to use 2 parameters because you need to compare 2 elements to figure out which is greater and lesser. So for example, we can force sort to sort of become partition by saying if return, we can reverse sort by saying A is greater than B. So what that's basically doing is we're saying, now you reverse sort things, now it's 9, 8, 7, 6, 5, 4, 3, 2, 1 instead. By just changing this, you can say, if you use bitwise add, you will basically sort based on the bit patterns, so now you have 0, 8, 7, 6, 2, 5, 4. No reason to do that. Or you can do like we did here, A mod B equals 0. It's not going to change anything. Like you can put whatever you want here that makes sense, but often you want to do this with structs where you want to sort by a particular member of the struct. So A is greater than that. Or if you want to reverse sort. But the other way you can reverse sort is also by using rbegin and rend instead, because then you get the vector in reverse, and then you also get the reverse sorted container because you're passing in the reversed iterators. Okay, so there's a lot of information, I realize that, but it's good to know this when you're going to work with it, so you don't have to fight against the language. So another one that's useful is find, so let's look at that right away. Find if is probably the most useful one, which means it finds that if some condition is true. So we start with, again, vector begin till end. And then you can write a function here that it takes a value, in this case just 1, and say we want to find a value where v is divisible by 7. So say now we're going to look for that, and it returns an iterator to where it is. So if we print divisible by 7, it's going to look through and it finds the number 7. So basically you can put, if you're looking for a specific value, you can use this, and these algorithms are generally recommended and writing the for loop yourself. So for example, instead of going every element in the vector, if e equals 7, then the return or use 7. Because you can write errors in there, but if you use this, you're explicitly saying that this is your intent and it helps you write correct code because it works. And what you get in return, you can use with all of the other algorithms, because now you can use this, for example, in another algorithm, or you can just use the value if that's all you want. If it's not there, that's important, because if it wasn't able to find it, so you have to check for that. So if it couldn't find it, then it will be equal to the end iterator. So if this one is equal to the end, it couldn't find it.
Okay.
Because it's at the end, basically. So you can say if it's not the end, then then it's safe to use it.
Is it also with if you write the beginning -1, it goes to the end?
No.
Oh, okay.
That's an illegal iteration.
Alright.
But so you have to check, and it's the same here. No, not here actually. But basically, you have to check if it's equal to the end, then it's invalid. Yes. Let's also quickly do accumulate. It's exactly the same as the other ones, except. Oh, by the way, all of these algorithms, you have to include algorithm to use them. Except for accumulate, which is in numeric. So if we just want to quickly use that, it's basically self-explanatory what it does at this point. So sum equals this. And we have to pass the start value, which is going to be 0. So if we do this, the sum of this vector is 45. So if you sum these numbers up, it's 45.
Okay. And the start value is like the one like
yeah, so
with
if you 5,
yeah.
then it's going to be 50.
Oh, okay.
Because you can say start at 5.
Alright.
It only works with integers.
It works with anything you can plus together. So if we put the string in here and push back the world, well, this one's not working. Okay, so we're now you got hello world, hello world, hello world, hello world, hello world. So it works with anything that supports plus operator. So you can override your own type to do that. Of course, now the rest of this is useless, but it accumulates basically all the values. So if you can plus them together, you can use the type. But it kind of makes the most sense with numbers in this case. Another one that's useful. It's map. And that you used with Python probably before, with either in the math course or somewhere else. But it's not called map, it's called transform. Right there. So transform is what applies a function to every element in the container. So it's like, in other languages this is called map, so let's put in the same parameters, v vector begin and end. So what we will put in here is so this needs an output as well, so we just put v vector begin, which means just override the value at the same location. So we're starting at begin to end, and we will write at the beginning and just keep going from there. So basically just overwrite the values. And again, we take a lambda, which is a value. So for example, if we wanted to double every number in the container, we would just say v. We have to take it by, no, we don't. We will return from here v times 2. So if we print the vector now, it will hold all the values doubled. So now we have 18, 16, 14, 12, 10 down to 0. So you can use transform to basically apply a function to every element in the container. So for example, if you want every vertex in the container to be multiplied by a matrix, or if you want every vertex to be change its color, you can use transform to just update those values. If you had a vector of vertices, and then you would take a vertex here instead, and just change the value, and that's how you can do that.
So the first beginning end says the range,
Yeah,
and then
so
the
transform from beginning till the end.
and then the second one. What was that one?
That means the result of this operation
Yeah.
will start being written out at the beginning as well.
Oh, okay.
So if you want to, for example, transform into a new vector, if you want to create a new vector result, and you want it to be equally big as this one,
Yeah.
then you can say that put the result in at the beginning of this vector,
Oh, okay.
which means you don't change the values in the original vector, you just take the result into the new one.
Oh, okay. All right.
So that could be nice to do now as well.
Yes.
That's probably for the algorithms. There's a link here if you want to see all of those that exist. There are a lot of them. So there's all of this. Yeah, they are useful, and usually there's something for everyone.
And these vectors and containers work on the vectors or the math vectors.
Yeah,
in
works on all of those things.
Alright.
There are some restrictions, but it's specified on each algorithm what the restrictions are.
Okay.
But if you use a vector, then every algorithm should be compatible because it's the most flexible container. Another reason why it should be your go-to container. Yeah, so this is basically what we just looked at live. And so let's look at some general tips. Here's that one, stop writing using namespace. Now that we're using a lot of libraries, maybe before you've been used to writing using namespace std, that has been fine-ish before. So of course if you do this, you can just use random shuffle, and you can just call sort directly or partition, which is very convenient and very nice of course when you're just doing it for example. But now that we are using a lot of libraries, consider for example if you did the same with using the namespace GLM. That means you can now just go back 3 v equals something. However, when you include GLM, you also have a function called max in GLM. And if you're also using namespace std, and you include, wait for it, math. What max function is this?
The maximum, it's like the highest value in a container. Like if you have
No, but like, which function are you calling?
Oh,
Are
yeah.
you calling
from
max
that
or GLM max, or are you calling?
like that.
It doesn't.
It does. Yeah, it's ambiguous, right? So. See, now it says return value is still max, but it also says that the call is ambiguous because there are multiple max functions. Because you are using both namespaces.
Yeah.
And since we are using multiple libraries that may have overlapping things, like for example, a lot of libraries can have init as a name or some other name. Don't do this because that creates a potential for bugs in your code. So in order for this to work, you can say you want a global max, which we'll call max in the global scope, or you can specify std max, or you can specify GLM max. But it's much better to not set yourself up for that failure in the beginning and just use the one you want to use from the beginning. What you can do if you want to, for example, use some algorithms without having to go stud in front of everything. Inside of the function you're going to use it, you can say using stud sort. Now you can just go sort directly.
More.
And that's a nicer way of doing it. So if you have a vector of integers again, containing some random values, now you can, because you're using sort inside this function only, you can now go sort. You can just do this.
Yeah.
So it's better that you just use it locally inside of a function instead of globally in the file. Technically here it would also be okay to use this one because it only applies to this function, no longer the entire file.
Yeah.
Sometimes it would also be okay to do this in a CPP file, but whatever you do, never do it in a header file. Yes, the question?
What is a template?
That was just a helper, so it's not really relevant. But basically, it allows you to write a function that works for multiple types. So you can make now.
Generic?
Yes, like that, just different. Templates in C++ are actually proven to be their own language. They are themselves able to solve all problems of programming, and so it's a huge topic on its own. And you can write a lot of fun things with it, but it's way beyond the scope. Anyway, so by introducing singular functions inside here instead, that's a lot better. So, but again, never using std namespace inside of a header file. That's like the biggest no ever, because everyone who includes that file will also be using namespace std, and that's going to break everything.
So if you find one, you're just going to fail that student.
Yeah, if you put it in the CPP file if you have to, and you really hate that std, but be aware that you are going to introduce a lot of potential bugs, and it's not that hard to either do this where you need specific types, or doing the std in front.
Yes.
So that's important. Yeah, avoiding raw pointers. Prefer using not pointers and references instead, because pointers come with a lot of errors, like null pointers, for example. So instead of, for example, making an int x equals 10, and then somehow deciding that I will write a function that takes an int pointer b and go with b plus equals 5. Yeah, so instead of forcing this and then allowing someone to put no pointer in there, just use a reference instead. So you can just because then it cannot be null. So and then you can pass x and you'll have the same. So prefer references over pointers unless. So references sort of indicate that this value cannot be null, and it needs to be something. Whereas a pointer indicates use pointers only when something can be null, basically, because references can't be. And prefer references and values over pointers, and you will avoid some errors, especially. Of course, with OpenGL, you have to work with pointers at some point because it expects pointers to a lot of its functions. So just be sure that, but you can't really get around that. So. Yeah, CPP reference is a great resource if you ever need to look up anything about the language. That's where we look at the algorithms. So you have all the headers, all the basic concepts, and everything you really need here. It's a good site, even if it's a little bit heavy on being a documentation thing. And use the tools recommended. So use the algorithm, use the vector. Don't write your own array that can be dynamically resized, because it's likely going to be less performant than the vector and less useful, unless you really like that kind of thing. In which case, that's on you. But these tools are really shown to you so you can focus on the graphics part and use them. So when you need to create arrays or add a lot of vertices and that kind of thing, it means you don't have to battle the language or battle having arrays that can be resized, so you can focus on just getting data to OpenGL and rendering it and writing all of that shade code that you need to do. So some graphics tips. Use a weird color for the background. So if you use green or pink or yellow as the background, that means, for example, if you're drawing a cube or a triangle, you will see if it's black. you will see if it's there even if it's black. So if you have a black background, you don't see if anything is there. If you have green background and something, and the model is drawing but it's black, then at least you see it's there even if it's black. So it's going to be easier for you to see mistakes. We are going to look at graphics debugging later, so we'll show you another way of doing it. Yeah.
How would you change the color of the background?
In lab 1 there's a function called the GL clear color, which you can which you use to set the background color. So we basically just call that anywhere. And I'll show it in here actually.
Sorry? I thought you meant the background, if you were to draw a triangle, the background that becomes black or white. Did you mean?
I meant just the screen, not the triangle itself. But I'll include the. So it's basically this function, and then you pass, for example, if you want it to be red or green for that matter. You basically put it to pure green, and now the background will be clear to green. So that makes it easier to see if you got something on screen, at least, because most errors it will be black, and then you don't see it if you have a black background. Or if you don't like to look at an obnoxious green, then pick a dark gray or something that is not pure black at least. Yeah, and OpenGL has error functions and error callbacks that you can use to get error messages and figure out what's going on. So if you forgot to call a parameter, if the parameter is wrong, if it's of the wrong type or something like that, you will actually get error messages back. This is only like the error callbacks are only available on OpenGL 4.3 and onwards. So if you don't support that, then you can't use those. But you can use the regular error functions, which we are going to introduce the GFX library at some point, probably, which has functionality for that. So we will show it to you later. But look it up. You can look it up yourself as well. But if you use the error functions or the error callbacks, you will be able to get sensible error messages, which will help you a lot as well. We can look at that in the debugging lecture. Yeah, so pay attention to debugging lectures. It will help you when something breaks, and it probably will sometime this semester because graphics comes with its issues. And so also debugging is harder on the GPU than on the CPU. So make sure your CPU code is correct first, just to avoid having to go through the hassle of debugging the GPU. And also focus on the problem you are solving and not what you think you're solving, and not over-engineering anything, because if you're trying to draw a triangle, don't create a graphics framework that's capable of drawing anything you could ever pass to it, and make sure that you can do all of these fancy things when all you're trying to do is draw a triangle. Focus on the problem, and then you can build on top of that and escalate as you learn more. And try to share resources. That's among yourself, of course, but this is mostly about when we get the textures or loading models. Try not to load the texture 5 times every time you need it, but like load it once into memory and then just refer to that texture later, so we don't waste your memory. Yes, so some typical mistakes that you might do this semester is, so for example, did you have the lecture about vertex buffers yet?
No, I'll have it on Tuesday.
Okay. So, well, basically, OpenGL uses a lot of resource handles that if you played a little bit with Lab 1, you will see that we have the GL create buffer function or something like that. Oftentimes people write classes that wrap around this, that like create it in the constructor and destroy it in the destructor, so you don't have to delete and create these objects yourself. Sometimes this can cause a lot of issues, because if you pass this object around, it might be copied and created as a temporary, and then that is destroyed, which destroys your OpenGL resource. And it's not so obvious that happens. So if you use an initialize or deinitialize function to do the initialize work of a constructor and a destructor instead, you can avoid this, but we will maybe look at this a little bit more in the debugging session when you have some experience with more experience with OpenGL. Also, size of mistakes that you may have already encountered when you were adding more triangles to the array, because sometimes because some OpenGL function take, when it says size, means the number of elements in the array, and other times it means the size in bytes. So make sure that you read the documentation. Docs.gl is a good site. It has, you can just type the function you want, for example, this one, and then you can look at it, and you see here, for example, it says size. And then you can see that it's the size in bytes, so make sure you put the right size. And sometimes it's the number of elements, sometimes it's the size in bytes, so make sure you check that to avoid errors. Also, later, there's a lot of similarly named functions in OpenGL. So, for example, you might end up using uniform3f instead of uniform3fv, or the other way around. So double check your function names, because this can screw you over. And then you also have variations of this again, with just one letter differences. So. One more thing, when you use pointers and vectors together, so again, if you have quickly a vector in, don't try not to have an integer pointer be the vector's third element. For example, try not to have a pointer to the third element in the vector. Try not to do this, because if we print this value now, that's fine, it's 5. But if we add some elements to this, let's make it 8 just so it's not 5, and do the same. It's now something else. First it was 8, then it's 21,940. So do not keep pointers into vectors, because when you add elements to the vector, it might reallocate and the memory have moved and the pointer is useless. So don't point into vectors. Instead of saving a pointer to it, save the index. So instead say index equals 3, because it will be the same. So don't use pointers to vectors, use the index number instead. Same with the iterators, don't save those either, because they... And I think that's about it. This is a free book with some game programming patterns that you can read. It's all on the web. So it has some nice chapters on some patterns, some game loop, which you're all gonna need